Today we are talking about empirical formula. What is empirical formula? Well, technically speaking, empirical formula as far as chemistry is concerned is the lowest whole number ratio of atoms in a compound. And the reason that we bring it up for ionic compounds is because that the vast majority of the time for ionic compounds, all you really need is empirical formula, because ionic compounds make these crystals, and these crystals are these recurring positive and negative. So again, you're talking positive, negative, positive, negative, positive, negative, all the way through these recurring three-dimensional structures of these cations and anions. And the reason that you need empirical formula only is because they repeat themselves over and over again. So it doesn't really matter what unit you look at. If you were to look at this box here, there is one positive and there is one negative in here. If you were to look at this one here, there are two positives and there are two negatives. And if you were to look at this larger box here, there are the same number of positives as there are negatives in this stuff. So you really don't want to have three different formulas. If this was sodium chloride, that would be NaCl. This one would be Na2Cl2. And this one over here would be Na8Cl8, but it's all salt. So for ionic compounds, you don't worry about how many there are. What you do is you worry about how many there are relative to the other ones. So if it's NaCl or Na2Cl2, it really doesn't matter for the vast majority of ionic compounds, whether it's 1, 2, or 8. It's just going to be 1, because it is the lowest whole number ratio between those guys. All right, so all you are doing is you are looking to see what the ratio is of them. And because of that, you can figure out what their percentages are, because they have a fixed formula, and you can know what the total, and then you can know what the parts of those things are. All right, so for example, in this one here, it says, it is determined that a chloride of iron is 34.4% by mass iron. What is the formula of the chloride of iron? So what I am going to do in this particular problem is I am going to assume that I have 100 grams of the substance. Why 100 grams of the substance? Because it makes math easy. I mean, you can pick 84.2 grams if you want, but you have to get a calculator and do some math on that. So pick 100, because if you're dealing with percentages, then it makes the math easy. So if I assume that I have 100 grams of FeXCl that's here, then if 34.4% of it by mass is iron, then that means that I have 34.4 grams of iron. And then if I get my calculator out for the chlorine, that would mean that I have 65.6 grams of chlorine that's there, because the two of those have to add up to be 100 grams. Now, at this point, your instinct might be to just say, well, then I'm going to call it Fe 34.4 and Cl 65.6. But that's a terrible choice, because the masses do not equal the moles or the atoms. So what these really are here are, these are ratio of atoms, or more appropriately moles, that are there. And the grams that we have here are not appropriate to use for those. So what you really need to do is you really need to take each of these masses that you have and convert them into moles. So get out your periodic table and look up where iron is on the periodic table, and you will discover that 1 mole of iron weighs 55.9 grams. And so if you do the math on that, you should end up with iron having a number of moles of 0.615 moles of iron, if you do the math on that correctly. Check your periodic table and look up chlorine. It is 1 mole per 35.5 grams. And if you do the math on that, you end up with 1.85 moles of chlorine. So again, when you go to solve these problems, if it's FeX and Cly, these here really tell you the number of atoms or moles that are there. And since we now have moles that are there, we can go ahead and plug those in. But when we do, it's going to look weird. This is 0.615, and this is 1.85 that is there. And clearly, we've never seen a compound that looks like that. These are always supposed to be whole numbers. So if they are supposed to be whole numbers, then what we are going to have to do is take these fractional numbers and turn them into relative amounts. Now again, this and this are already a relative amount. For every 0.615 that's here, there's 1.85 of them that are over here. But we don't want fractional numbers, we want whole numbers. So how do you take a fraction and turn it into a whole? Well, the easiest way to do it is to simply divide by the smallest number. And the smaller of the two numbers here is the 0.615. So I'm going to divide this by 0.615. And when I do, obviously, I turn out to get a 1. But if I then divide this by 0.615, then that turns out to be right at about 3. So what is the actual formula for this substance? It's FeCl3, which would mean then that for every 1 iron that is present within that ionic crystal, there are 3 chlorides present within that crystal. And this is the empirical formula, which is the lowest whole number ratio of the atoms, a 1:3 ratio. Let's try one more. This one here says it's determined that an oxide of copper has a mass of 88.8% copper, and what's the formula for the oxide of copper? So again, I am going to assume I have 100 grams of CuXOY that is there. So that means that I have 88.8 grams of copper, and I have 11.2 grams of oxygen. You get out your periodic tables. Oxygen weighs 16 grams, and copper weighs 63.5 grams for a mole. So you end up with copper being 1.4 moles of copper, and you end up with oxygen being 0.7 moles of oxygen. So your formula is Cu 1.40.7 that's here. But just like we saw in the last problem, that doesn't work. We need to get these into whole numbers because that's the way we'd like to represent these compounds. So consequently, we are going to divide by the smaller of the two numbers, which is 0.7. And we end up with Cu2O1 or Cu2O as its formula. That is there.